Solving quadratic equations and inequalities. Given f of x equals ax squared plus bx plus c, a quadratic, to determine where f of x equals 0, or to solve a quadratic equation, we can try to factor to solve. If not factorable, we can use the quadratic equation. The real number solutions are x-intercepts of the quadratic f of x. To determine where f of x is less than or equal to 0, less than 0, greater than 0, or greater than or equal to 0, or to solve a quadratic inequality, we will need to find the real solutions to f of x equals 0, or the x-intercepts, and then determine on what x intervals f of x is positive, above the x-axis, or negative, below the x-axis. We will review two different ways to do this, either graphically or analytically with a sign chart. In this example, we want to solve the equation x squared minus 4x minus 12 equals 0. Well, we have the quadratic on one side and equals 0 on the other side, so we should first try to factor. And this is fairly straightforward to factor because the leading coefficient is 1. So we can go ahead and factor this to be x minus 6, x plus 2, is equal to 0. So if we check, outer is plus 2x and inner is minus 6x, so that will add to be negative 4x. And we are solving, so we set each factor equal to 0. So we'd get x equals positive 6 and x equals negative 2. So our two solutions are negative 2 and positive 6. Alright, so now we move on to solving the inequality. So the inequality x squared minus 4x minus 12 is greater than or equal to 0. We want to solve this first by graphing. Well, the first thing we do need to do is solve the equation for the real zeros, for the real number solutions, because those are going to be the x-intercepts. So here, the first step would be to solve the equation x squared minus 4x minus 12 equals 0, of which we know negative 2 and 6 were the solutions. But what that means, what that implies, is that negative 2 comma 0 and 6 comma 0 are x-intercepts. So if we want to solve this by graphing, well, we have x-intercepts. We can go ahead and graph them. So we have negative 2, 0, and 6, 0. And this is a quadratic which will graph a parabola that opens up because the leading coefficient is 1. Now the nice thing is that we only need a really rough sketch of the graph. So when we say by graphing, all we really need is the x-intercepts and the general shape. So whether it opens up or down. So we have the x-intercepts. We know that it opens upward. So I'm going to go ahead and just sketch this upward facing parabola here. So we want to go ahead and interpret this greater than or equal to 0 on the graph. So that means I want to know when I'm above or on the x-axis, right? 0 is the x-axis. So if I want to figure out where am I above or on the x-axis, I'm going to go ahead and shade those pieces and then describe them using intervals. So these are x intervals where we're describing where the graph is above or on the x-axis. So that's going to happen on the interval negative infinity to negative 2, closed bracket, because that's where I'm on the x-axis, and 6 with a closed bracket to positive infinity. So all of the numbers in these two intervals, when substituted into x, on the left side into this quadratic, that's going to give me a number either greater than or equal to 0. In the third part of this example, we want to solve the same inequality x squared minus 4x minus 12 is greater than or equal to 0 analytically. And this means by creating a sign chart. So we're going to pretend we haven't even done this problem at all. So what we would do is we would start out by setting the quadratic equal to 0. So even though it's an inequality, we do have to try to set it equal to 0 to find its real solutions, if it has any. So here we did do this work before, so we said x minus 6 times x plus 2. So we got out negative 2 and positive 6 as solutions. All right, so now we're going to go ahead and create a sign chart. Now a sign chart is constructed by creating a number line. And the number line is going to extend over the domain of the function. So the domain of the function, the domain of any quadratic, is all real numbers. So negative infinity to infinity. And we're going to put these real number solutions onto the number line. So negative 2 has to go first, and then 6 next. So we always go from least to greatest. And I like to go ahead and above each one of those put a little z to remind myself those were zeros of the function. Now what we need to do is figure out over each interval, so from negative infinity to negative 2, and from negative 2 to 6, and from 6 to infinity, what is happening to the function? Is the function positive or negative over each of those intervals? So we are interested in the sign of the function. Let's call it f of x. So let's go ahead and say this function here was f of x. So I'm interested in the sign of f of x. And in order to determine that, the easiest thing to do is to consider f of x as its factored version. So I want the sign of quantity x minus 6, quantity x, plus 2. So in order to determine the sign, we're going to pick a test point value in each interval. So within each interval, I'm going to go ahead and pick a test point. So between negative infinity and negative 2, I can pick any number, but I'm going to go ahead and pick like the nicest integer that's to the left of negative 2. So I'm going to go ahead and pick negative 3. So up here, these are going to be my test point values, my testing values. Between negative 2 and 6, well, the easiest value to choose would be 0. 0 is definitely between negative and positive. And then between 6 and infinity, I'm going to go ahead and choose 7. So these test points, what we do is we substitute them into the function. I want to know the sign of the function. Is the function positive or negative? So here, negative 3, if we plugged it into the original function, I'd actually have to do a lot of work. Well, I'd have to do negative 3 squared minus 4x minus 12 and think about if that overall number is positive or negative. The benefit of using the factored version is I can go ahead and think about each factor's sign separately. So if I plug in negative 3 minus 6 is going to give me a negative value. Negative 3 minus 6 is negative 9. But I don't even have to care that it's negative 9. All I'm going to do is put that it's a negative. So this first factor is negative, and then negative 3 substitute into x plus 2 is going to be a negative 1. So I have a negative times a negative. Well, a negative times a negative is a positive. So this first interval from negative infinity to negative 2 is a positive interval, and we wanted positive interval, so greater than or equal to 0. So part of my answer, I'm going to start writing it already, part of my answer will include this interval from negative infinity to negative 2. So negative infinity to negative 2. Now the reason why I put a z above negative 2 is to remind myself that's where I was equal to 0. And I want to know when am I greater than or equal to 0. So I am going to include that negative 2 value. Then we move on and check the next test point. So 0 minus 6, that's going to be negative, but 0 into x plus 2 is going to be positive. We know a negative times a positive is overall a negative. So I don't want that middle interval. I don't want to include all the numbers between negative 2 and 6. And then finally, I go ahead and test 7 into each factor. 7 minus 6 is positive, and 7 plus 2 is positive. So I have a positive times a positive. Overall, I have positive. And again, I wanted to know when am I greater than or equal to 0. So I want positive intervals. So I do want to include the interval from 6 to infinity. 6 was where I was equal to 0, so I want to go ahead and include 6 and go all the way to infinity. And we did do this graphically, so we know that this confirms the same answer. On this example, we're going to go ahead and solve the equation x squared plus 1 equals 0. Well, x squared plus 1 is the sum of squares, which we know doesn't factor. But in order to solve this equation, we can use the quadratic formula, but because there's no middle term x here, like a bx term, we can also just go ahead and subtract the 1 to the other side, so we get x squared equals negative 1. And when I take the square root of both sides, I'll get plus or minus the square root of negative 1, which should give us some sort of red flags because a negative underneath the square root is an imaginary number. So what we have is plus or minus I. The imaginary number I is the square root of negative 1. So this does have solutions. This has the two solutions, negative I and positive I. However, those are not real numbers. So these are solutions, but they are imaginary solutions or complex number solutions. So now when we go to part B and we think about the inequality, solve the inequality x squared plus 1 is greater than or equal to 0. Well, here we have two choices. We can solve this graphically, or we can solve this analytically, so using a sign chart. So if we think about this graphically, we know that there's no x-intercepts because there's no real number solutions to this quadratic equation. But that doesn't stop us from graphing. In fact, graphing is pretty straightforward. So the graph of x squared plus 1 is just going to be the graph of x squared shifted up 1 unit. So everything's going to shift up 1 unit. I'm just going to do a rough sketch here. So if I were solving this graphically, when is x squared plus 1 above or on the x-axis? Well, it's always above the x-axis. So the solution is all real numbers. I'm solving for what x values can I plug in to give me positive outputs. Well, I can plug in absolutely any x value. So my answer is negative infinity to infinity. So all real numbers. Now, if I didn't draw the graph, I could still approach this analytically and do a sign chart, but my sign chart would be really boring. I would have negative infinity and infinity, the domain of the function, but I wouldn't have any zeros on here, right? I wouldn't have any x-intercepts. There's no real zeros. So I could pick a test point, any test point I want, like 0 is probably the nicest test point, and I would substitute that test point in to find the sign of f of x, or the sign of, let's just say, x squared plus 1, the function. Now if I plug in 0, 0 squared plus 1, that's going to give me 1. That's going to give me positive. So on the entire number line, my outputs are positive. So again, just confirming, the answer is negative infinity to infinity. Now before we move on, just real quick, I actually would say that none of this work was necessary if I really understand the concept here of this inequality. We're asking ourselves, what x values can I plug in so that when I square them and add 1, that's going to give me a number that's greater than or equal to 0, or positive. Well, anytime you square something, you're going to get out a positive answer, and then you're just going to add 1 to it, so it's going to stay positive. So that's why the solution is all real numbers. In this example, we want to solve the inequality 2x squared is less than x plus 10, both analytically and by graphing. So this is slightly different because I don't have a quadratic less than 0, but I'm going to have to create that situation. I do want that to move forward, and I'm going to accomplish it by subtracting the x and subtracting the 10. So we actually want to solve the inequality 2x squared minus x minus 10 is less than 0. So to start this problem, we're going to do it analytically. We do need to solve the equation first. So we need to know, when is 2x squared minus x minus 10 equal to 0? We want to try to go ahead and solve by factoring. So we're going to have a 2x and x. That's the only way we can go ahead and get 2x squared. And then to get negative 10, well, we can use either 10 and 1 or 5 and 2. The values that I'm going to go ahead and use here are 5 and 2. If I go ahead and put a 5 right here, that's going to make the inner 5x. And if I put a 2 here, that's going to make the outer 4x. And so I just need the signs to work out to get a negative 1 in the middle. So I'm going to need the 5x to be negative and the 4x to be positive. And then last is going to give us negative 10. So this is my factorization. It's going to leave us with the real zeros, x equals 5 over 2, because I'm going to set this equal to 0. I would add the 5 and divide by 2. And then here I'm going to get x equals negative 2. So these are my real number solutions. So, I mean, we could take the time to put them in squiggly braces, but this was honestly just scratch work, because we're going to now go ahead and put them on my number line. So my domain of any quadratic, negative infinity to infinity, I'm going to put negative 2, positive 5 over 2, remind myself that these were zeros. And then what we're interested in is figuring out, well, over each interval, what is happening. So we have to pick a test point in each interval to determine the sign of the function. So my test point here, we'll go ahead and pick negative 3. So TP is going to stand for a test point. Between negative 2 and 5 over 2, we'll pick 0. And 5 over 2, well, that's 2.5. So a number bigger than 2.5, that's pretty nice to work with, is just 3. And we're interested in the sign of the function. Now, the function is 2x squared minus x minus 10, but it's always going to be easier to use the factored version in our sign chart analysis. So we want the sign of the factored version, 2x minus 5 times x plus 2. So substituting in negative 3 into each factor, we would get, well, negative 3 times 2 is negative 6 minus 5. So that's going to give me a negative 11 or a negative. Negative 3 plus 2, well, that's negative 1. So another negative. A negative times a negative is a positive. Now, do I want positive numbers? Let's see. I wanted to know where is the function, the original function, the factored version, right? Doesn't matter. Where's the function less than 0? That means negative. I want negative intervals, right? So this less than over here means that I want negative intervals. So I do not want to include this first interval. So then we go ahead and move on to substituting in 0. 2 times 0 minus 5, that's going to give me a negative. 0 plus 2 is going to give me a positive. So a negative times a positive is a negative. I do want to include this interval. So this interval goes from negative 2 to 5 over 2. And we do not want to include those numbers because I want to know where am I strictly negative, not where am I negative or equal to 0. So in my answer, I want to use open parentheses, negative 2 to 5 over 2, open parentheses. So any number in this interval will work in this inequality. 0 was just a test point that we chose, and so any value will follow the same behavior as that test point. And then finally, when I plug in 3, 2 times 3 is 6, 6 minus 5 is positive 1, 3 plus 2 is another positive, so this interval is positive. We do not want to include positive intervals, we want negative ones, so here is my answer. Now let's go ahead and confirm this by graphing. So to have solved this by graphing, we still would have had to set the equation equal to 0 and get 5 over 2 and negative 2, but we would have interpreted them. We would have thought about, well, these are x-intercepts, right? So 5 over 2 comma 0 and negative 2 comma 0 are my x-intercepts. So we'll go ahead and plot negative 2, and then 5 over 2 is 2.5. These tick marks are by 2s, so you have to be careful. And then this parabola, we just need the general shape. So my parabola is going to open upward here because the leading coefficient is positive 2. And so we're going to go ahead and sketch this upward facing parabola. That wasn't quite right, so I'm going to try one more time. Probably a little something like this. I tried to actually make it kind of accurate. Let me move it over. I do know the y-intercept is -10, although I don't need it, right? So that's additional information. If I were being asked to graph a comprehensive graph of a quadratic, I do want all the intercepts, but I'm using this graph to determine where am I below the x-axis. So we could think about this as less than symbol as negative when I do a sign chart. But what I really want on a graph is to think about where am I below the x-axis. Well, I'm below the x-axis between -2 and 2.5. That's how we got this x-intercept. It was 2.5. So that is what I'm going to describe as an x-interval, which of course we already have because we did the problem algebraically. Now, before we move on completely from this topic, I want to talk about a common mistake. So this is the same problem as the last one. I'm going to talk about a huge warning. So sometimes what students do is they go ahead and subtract the x and subtract the 10 to the other side, and then they go ahead and factor correctly. So we said this factors to 2x minus 5 and then x plus 2. And then they try to treat it like a quadratic equation. And in a quadratic equation, we can take each factor and set it equal to 0. So what they try to do is take 2x minus 5 less than 0 and x plus 2 is less than 0. Unfortunately, that is an incorrect way of trying to solve an inequality. So the only option for doing this analytically is creating a sign chart. So there is something called the zero product property, and we can only use it to solve equations. So when I have a product, I can only set it equal to 0. I can't set each factor less than 0. It's going to give me the wrong answer. So just a warning about that. I can only set factors equal to 0, not less than or greater than or equal to or less than or equal to. That is not how to solve any inequality analytically. In this example, a farmer had 2,000 yards of fencing and wishes to enclose a rectangular area, as seen here. Part A expressed the area A of the rectangle as a function of x. Well, the area of a rectangle is base times height, and the base of this rectangle is going to be 2x total, and the height is y. So the area so far as a function of x and y is 2x times y. Well, we want it to just be a function of x, so we want to go ahead and eliminate the y. So we're going to use the 2,000 yards of fencing piece of information to solve for y in terms of x. So the 2,000 yards of fencing is going to be used to create the total perimeter, including this separating bar in the middle, or fence in the middle. So we know that 2,000 is going to have to equal a total of 4x, so 2x on the bottom and 2x on the top, so 4x plus a total of 3y. So vertically we have 3 copies of y. And so now we can solve this equation for y in terms of x. So I can subtract the 4x to the other side. So 2,000 minus 4x is equal to 3y. And then divide everything by 3. So y is going to be equal to 2,000 over 3 minus 4/3 x. And we'll go ahead and substitute that in over here to get area as a function of x is 2x times 2,000 over 3 minus 4/3 x. So this is my area of the rectangle as a function of x. Now we're going to do something with this. In part B, we're asked for what value of x is the area the largest. For what value of x is the area the largest? And then what is the largest area that can be enclosed? So here, we didn't go ahead and distribute in the x, so maybe we can't tell, but this area function is a quadratic. So if I were to go ahead and distribute it, so here I'm going to go ahead and say a of x is 4,000 over 3x minus 8/3 x squared. So distributing in this 2x, I can see this is a quadratic equation. So the question is, for what value of x is the area the largest? Well, for largest on a quadratic, we're thinking maximum, which happens at the vertex. So essentially, this is asking me for the x value of the vertex. Now, we have a formula to find the vertex, hk. So to find the value of h, the formula is negative b. Well, b is the number in front of x, so we want to be careful. That's going to be 4,000 over 3. So we have negative b, 4,000 over 3, over 2 times a. Well, a is the value in front of x squared, which is negative 8/3. So that's going to give me negative 4,000 over 3 times, now on the bottom I have negative 16 over 3 if I multiply, but I'm going to multiply by the reciprocal. Instead of dividing by negative 16 over 3, I'm going to multiply by 3 over negative 16, so that the 3 cancels, and then I'll go ahead and reduce this to its lowest terms, which is 250. So for what value of x is the area the largest when x equals 250, and that's going to be 250 yards. So that's going to answer the first part of this question. And the second part of this question is, well, what is the largest area that can be enclosed? Well, we know what happens when x is equal to 250 yards, and the area itself is what happens when you plug an x value in, so I'm just going to substitute 250 into each x here. So essentially it's like asking to find k. So what is a of 250? That will give me the largest area. So that's 4,000 over 3 times 250 minus 8/3 times 250 squared. And that value ends up being 500,000 over 3 yards squared. So remember that the output would be an area. An area has units that are squared, but the input is just x, right? X is one of the sides of the fence, so that's just in yards. And then finally, part C, what are the dimensions of the rectangle that enclose the most area? So here, the dimensions, well, when we think about dimensions, we think base times height. So here, we know that x is 250, so I'm going to come back up here. X was 250, so this is 250. So total, the base is 500 yards. And then what about y? Well, what did we know about y? Y was equal to this 2,000 over 3 minus 4/3 x. So we already know what x is. X is 250. So here, if I go ahead and think about, well, y is going to be 2,000 over 3 minus 4 times 250 over 3. That's going to simplify to 1,000 over 3 yards. Oops. So when we think about dimensions, we say, you know, base times height or length times width. So the dimensions are 500 yards by 1,000 over 3 yards. So I'm choosing to leave my answers exact because I know if I divide, if I divide 1,000 by 3, it's not going to give me a nice number. It's going to be something I have to round, so I'm just leaving my answers here exact. In this example, a projectile is fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal, with muzzle velocity of 400 feet per second. So if we take a look at the corresponding graph, we have that the projectile initially started at a height of 500 feet above the ground because it's on a cliff, And here it's just showing that that original angle was 45 degrees, and they're telling you that its initial velocity was 400 feet per second. So from physics, the height, h, of the projectile above the water can be modeled by this equation. So negative 32x squared over 400 squared, so this is a physics formula where we're plugging in the initial velocity, plus x plus 500 feet, that's the initial height, where x is the horizontal distance of the projectile from the base of the cliff. So x, this here, is the distance, how far I am from this cliff over here. Part A is find the maximum height of the projectile. Now, the picture really shows what we're looking for here. We're looking for how high does it go? Well, that's going to be the y value of the vertex. So up here, that's going to be my vertex, my hk. So the maximum height is the y value of the vertex. And this is, of course, a quadratic. So we have that formula for a vertex. So to find the x value of the vertex, I'm going to go ahead and call it h. I'm going to call it x instead of h because the name of the equation is h. So x is going to be negative b, so the value of b is 1, so negative 1 over 2a. And the value of a is negative 32 over 400 squared, so the number that's in front of x squared. So we have negative 32 over 400 squared. So that's negative 1 over negative 64 over 400 squared. And if I go ahead and flip that, I'm going to get 400 squared over 64. The two negatives cancel, multiply by the reciprocal. This ends up being 2,500. Whoops. So now we need to find the corresponding y value. So y is equal to h of 2,500. We wanted the y value of the vertex, right? This is like finding k up here. So we're going to go ahead and plug that into the function. So into negative 32, and we have 2,500 squared over 400 squared plus 2,500 plus 500. And obviously we're plugging this into a calculator, and this would give me 1,750. And here we're talking about height, so find the maximum height. The units were feet, so 1,750 feet. So it's really, this problem is a fancy way of saying find the vertex, or specifically find the y value of the vertex. Now in part B, how far from the base of the cliff will the projectile strike the water? So over here, if we think about the path of the projectile, it's going to strike the water when I'm on the x-axis, if I look at the model on the y plane here. So I want to know, essentially, the x-intercept of the function. So to find x-intercepts, we set the function, or the y value, equal to 0. So I'm going to go ahead and solve, when does this function equal 0? So when does 0 equal this negative 32 over 400 squared, x squared, plus 1x, plus 500. And I'm writing it like this so I can clearly see my values of a, b, and c, because although I'm solving a quadratic equation, I'm definitely not going to do this by trying to factor. I'm just going to jump straight to the quadratic formula here. So the quadratic formula, we have negative b, negative 1, plus or minus the square root of b squared minus 4 times a, it's negative 32 over 400 squared, c, so 500, all over 2a, so 2 times 1. And after kind of simplifying this and plugging into the calculator, we get two solutions, right? Plus or minus, this is definitely not 0 here, so we're going to get two solutions. And I'm going to go ahead and present those two solutions here. One of them is negative 458, and the other one is 5,458. So let's go ahead and think about that. Well, we can see that the y-intercept here is 500, but the parabola itself would keep going. and have another x-intercept. But we don't consider anything to the left because this is, of course, where the cliff is. So the only x-intercept we're interested in is the one that's obviously bigger than 5,000. So 5,458 feet, that is how far I am from the base of the cliff before the projectile strikes the water. So it's gotten 5,458 feet away before it strikes the water. So the only sort of last thing I'm going to mention here is this problem really captures why we're interested, why we say that a comprehensive graph includes the y-intercept, the x-intercepts, and the vertex, because we can see, well, at the vertex, that's when our maximum height occurred, which we would be interested in a lot of different applications, right? So here something's being thrown into the air. So we're interested in the highest point, which is the vertex. The y-intercept was the initial height of the object, which played a part in the problem. And then the x-intercept was, again, how far I was from the base of the cliff when the projectiles hit the water. So that's why when we draw a parabola, we say the comprehensive graph includes those components, the x-intercepts, the y-intercept, and the vertex.